In the last video, I introduced this new topic called related rates, and I don't even know if introduced is the right verb to use. I kind of just threw an example at you and solved it in front of you. That's a different teaching strategy than we've used so far in the class. The reason why is related rates doesn't really do anything new calculus-wise. It's really just an application of something you already learned, namely implicit differentiation. But as I mentioned, even though it's not doing anything new, the problems can still be fairly challenging, especially if you haven't already solved a problem similar to the one that's being asked. So what I want to do in this series of videos is just give you a whole bunch of examples. Last time we did one about boats traveling perpendicular to each other. In this example, what we want to talk about is a balloon being inflated. So we have a balloon that we're assuming is spherical, and we're inflating at a rate of 5 cubic centimeters per minute, although I think what you'll find is typically I don't care a whole lot about units here, but it's not a bad idea to keep track of the units as you're going through. The question is, at what rate, so you're thinking derivative, is the diameter of the balloon changing 2 minutes after the inflation starts? So if you read through the problem, we're given this number 5, and this is some sort of rate of change. This will be something prime. We're asked about the rate at which the diameter of the balloon is changing. So I don't know, maybe we call d the diameter of the balloon, in which case d prime would be what we're looking for in this problem. And we want to know d prime 2 minutes after the inflation starts. So presumably the balloon starts out with a volume of 0, and we're pumping air into it at this rate. So after 2 minutes, there's a certain amount of air in the balloon. The balloon has a given volume. The point that I'm trying to make is the letters that are related together here are the volume of this balloon and the diameter of the balloon. You probably don't have memorized the volume of a sphere formula. It's something that I'd provide you with if I were to ask you a question like this on a test. It's 4/3 pi r cubed. This gives the volume of a sphere with radius r. Unfortunately, in this problem, we're not talking about the radius, we're talking about the diameter, so it might make more sense to use the formula 4/3 pi, and then instead of writing r cubed, we could write d over 2 cubed, because the radius is half of the diameter. Here's a formula that maybe you'd be provided with if I was being kind of a jerk, and here's a formula that you'd have to come up with from this provided formula once you recognize that it's the diameter that's changing in this problem. This formula relates together V, the volume of the balloon, and D, the diameter of the balloon. D prime is what we're trying to figure out, and this 5 right here talks about the rate at which the balloon is being inflated. Even though you're not explicitly told, you're supposed to recognize that this 5 right here would be V prime, the rate of change of the volume. So we have this equation set up that relates together the two letters that we're either told about the rate of change of or wanting to determine the rate of change of. So here's where we do our calculus. Take the derivative of both sides of the equation. I need the derivative of v on the left side, and I need the derivative of 4/3 pi times d over 2 cubed over here on the right side. The derivative of the left side is pretty straightforward. The letter v represents a function. Its derivative we'll use the symbol v prime to represent. The right side's a little bit more challenging. What you want to recognize on the right side is that we have some coefficients. The 4/3 and the pi are both coefficients here. We can pull those out in front of the derivative symbol and get 4/3 pi times the derivative of d over 2 cubed. We're not done with the calculus because we still have this d over dt symbol. So now we try to take the derivative of this. It's a little bit challenging. It'd be nice if you saw some chain rule going on in here. What we have to do first is recognize that the outer layer in this composite function is the 3 up here in the exponent. Stuff being cubed is my outer function. So I bring that 3 down in front, leave the inner layer, the d over 2, completely alone, and then subtract 1 from that exponent to make it a 2. But then I'm not done. I still have to multiply that by the derivative of the inner layer, d over 2 in this case. If you want, you can just copy everything down, or it's not a bad idea to simplify where you can. This 3 and this 3 cancel out, so what I'm left with is just 4 pi times d over 2 squared times whatever the derivative of d over 2 is equal to. Well, if you think about this d over 2 as 1/2 times d, then you can pull the 1/2 out in front of the derivative symbol, and all that'll be left is to take the derivative of d. If you do things this way, the calculus becomes pretty easy. I'll leave everything else alone for the meantime. Take the derivative of d, because d is a function, its derivative is d prime. I want to solve for d prime, so you could just divide all this stuff over to the other side of the equation. although I think it'll make your life a little bit easier if you clean stuff up first. D over 2 squared is the same as d squared over 4, if I square the top and the bottom of that fraction. And now I have a 4 up in the numerator and a 4 down in the denominator, so I can say that v prime is equal to pi divided by 2, this 4 and this 1/4 are gone, times d squared times d prime. Now to get the d prime all by itself, I'll multiply both sides by 2 and then divide by pi d squared, and I get that d prime is equal to 2v prime divided by pi d squared. I know I ended the last video by saying the calculus typically isn't that hard in these problems. This might be a bit of an exception. That calculus wasn't easy for sure. You might be able to do this in less steps than I showed, but I also know that it'd be really easy to make a little mistake in your process. So I really tried to show all the different steps to hopefully make the calculus steps for you pretty clear in here. What I now have is d prime solved for. Remember, my question is, what is d prime? But not d prime at any time, d prime 2 minutes after the inflation starts. What I need to know to figure this out is I need to know what v prime is equal to, and I need to know what d is equal to. I know v prime, but I don't know d. What d represents is the diameter of this balloon 2 minutes after the inflation starts. I don't know what that's equal to, but I do have this equation that relates together the volume and the diameter. And since the balloon is being inflated at a rate of 5 cubic centimeters per minute, I know that after 2 minutes, the volume is equal to 10. I don't need to know v for this equation, but I can use the fact that v equals 10 to figure out what d is equal to. 10 must be equal to 4/3 times pi times d over 2 cubed. To solve this equation for d, maybe you'd get rid of the parentheses first. I got 4/3 pi times d cubed divided by 8 if I cube the top and the bottom of these parentheses. Now I can cancel out this 4 with kind of half of this 8, and that leaves me with 10 equals pi d cubed, because the 4 is gone, divided by 6, this 3 times the 2 that I'd have left over here. Now I can figure out what d is equal to. If I multiply both sides by 6 and divide by pi, I get 60 over pi is equal to d cubed, and therefore d is equal to the cubed root of 60 over pi. You could throw that into a calculator if you really wanted a decimal approximation, but I kind of prefer to leave my answers exact, so I'm going to leave d as this expression. This is some number. I don't really care what the number is. If you care, toss it in a calculator. The key thing now is I have all the information I need to figure out my answer. Remember, d prime is equal to 2v prime divided by pi d squared. So I have 2 times whatever v prime is equal to. Remember, that was given in the problem to be equal to 5, divided by pi times d, which is this expression, the cubed root of 60 over pi, squared. Clean this up a little bit if you feel like it. 2 times 5 is 10. Maybe I'd write it as 10 divided by pi times 60 over pi raised up to the negative 2/3 power. Negative because this 60 over pi is down in the denominator. 2 because this thing is being squared. Thirds because I'm taking the cubed root. There's plenty of other ways you could write this, but maybe I'm going to call that good. If you want a reasonableness check, we could take this expression and type it into a calculator. I got 10 over pi times 60 divided by pi raised up to the negative 2/3 power. Desmos tells me that that's approximately 0.446, I guess, if I'm rounding to 3 decimal places. I guess since my units are in cubic centimeters up here, my diameter would be in centimeters. So what this is saying is the diameter of this balloon is increasing at a rate of about 1/2 centimeter per minute if the volume is increasing at 5 cubic centimeters per minute at this instant 2 minutes after the inflation starts. I can just tell you that I'm not super worried about decimal approximations, nor am I worried about units. So for the purposes of our class, if you can come up with this numeric expression that represents the answer, I'm thrilled. As is typically the case with related rates problems, part of the challenge is just coming up with the equation that relates together the different functions that are given in the problem. I don't want this to become a geometry class, so expect me to provide you with equations like this one or the one that you see down here. The other comment is when you're reading these problems, expect some of the things that you're going to end up plugging into your expression to be given to you, v prime in this case, but often it's the case where some of the things, d in this case, are not given to you, and you have to use the equation, which will typically be provided in these geometry problems, to solve for that other letter that you need to plug into your answer.